Hello everyone. I'd like to welcome you all to the next and final installment of Spex Certiprep's webinar series on BPA and phthalates in imported plastic toys. The webinar we have lined up for you today is part 2, the extraction and determination of BPA and phthalate content in imported plastic toys. First, I'd like to introduce myself. My name is Matt Snyder, and I am the Marketing Associate here at Spex Certiprep, and I'll be moderating the presentation today. So before we begin, I'd just like to get a few housekeeping items out of the way. First off, everyone in attendance today will be receiving a copy of the presentation slides. Also, the webinar is being recorded and will be posted to our YouTube account about a week after the event. Questions will be answered towards the end of the presentation. If you have any questions during the presentation, simply type them into the question box on your screen, and we'll get to as many as we can during the Q&A session. We also have a representative, Bill McLucky from CEM Corporation, on the line with us. So if you have any questions pertaining to microwave methods, microwave extractions, feel free to direct your questions to Bill. So with those items out of the way, I'd like to introduce our presenter for today's webinar. Pat Atkins is Product Application Specialist here at Spex Certiprep, who you probably remember from a number of previous webinars, including part 1 of this webinar series. So without any further ado, Pat, I'll pass the mic to you.
Thank you very much, and welcome everyone. Welcome to the second and final part of our series on phthalates and BPA in children's toys. And thank you to CEM for joining us this afternoon. Feel free to type in any questions you might have for them as well, and we'll direct them to Bill as the webinar goes on. As of last week, in preparing for this webinar, I wanted to see if phthalates were really still a hot topic in the news. And as soon as I kind of Googled phthalates, I came up with this article that was published last week in the Science Daily. It's about phthalates in PVC floors being taken up by the bodies of infants. So even now, the whole question of phthalates in children and their exposure is still being examined, and is still a very hot topic. This is a chart of some of the most common phthalates in use, and the ones in particular that are being regulated right now are these 6 phthalates, starting with the di-n-butyl phthalate and going through this di-isononyl phthalate. Also in preparing for this webinar, I found this very interesting table in a report about phthalates and risk assessment, and it has some of the very interesting uses for some of these phthalates. So some of them that stuck out in my mind were uses in insect repellent, shampoos, cosmetics, soaps, lotions. So that in almost every type of product, there is some sort of phthalate being used. For children, there are many routes of exposure for phthalates. Medical devices are a good possible route, especially for sick children. They can contain up to 20–40% of DEHP by weight. And certain medications, certain pills and tablets actually do have a phthalate coating on them. Child care products like diaper creams, lotions, shampoos, ointments, they also may contain phthalates. Then, of course, the topics of conversation for us today, children's articles like pacifiers, bottles, plates, spoons, and children's toys. As far as regulations go, the U.S., the EU, and Japan have placed restrictions on 6 particular phthalates. For the U.S., these restrictions are on at 0.1% of each of these phthalates, individual phthalates. For the EU and Japan, it's 0.1% combined total for all of the phthalates. On the right side of the screen, there's a set of phthalates, the DINP, the DIDP, and the DNOP, that are highlighted in orange. The restriction is for these phthalates in oral contact items. So toys and child care items that are meant to go in the mouth have these particular limits for these 3 phthalates. On the left side, the DEHP, the DBP, and the BBP, these are across the board controlled in children's toys and children's child care articles, whether they are oral contact or not. As far as bisphenol A, children can be exposed to bisphenol A in a multitude of different ways as well. Things like food and food packaging, can liners, containers, most notoriously baby bottles. A few years ago, a study was done that showed up to 13 micrograms per kilogram of body weight per day of BPA was from exposure to baby bottles. Of course, we know about water bottles and sports bottles, especially the polycarbonate bottles having BPA. There was also another study that showed liquid baby formula could contribute between 0.48 and 11 nanograms per gram of formula for BPA. Some unlikely sources of BPA exposure that we might not think about are receipts and labels. There was a study about 2 years ago that showed that those thermal labels and those thermal receipts like you get at fast food restaurants or at your chain stores, those labels have free BPA coated on them. So that free BPA can be easily transferred to the hands, the face, the mouth, especially with children who are always putting pieces of paper and other things in their mouth. You also have PVC piping, which is a route of exposure to BPA for children. Again, medical devices, and finally, our toys. An interesting, very small study that I found from the U.S. in 2009 showed that BPA exposure for infants actually starts in utero, that starts during pregnancy. They tested cord blood from 10 babies, and they found an average of 2.8 nanograms per milliliter of BPA in the cord blood. As far as regulations go for BPA, there is no nationwide ban here in the U.S. for BPA, and there are state-to-state bans, usually for various child care products like baby bottles and feeding utensils. In the EU and Canada, polycarbonate baby bottles are banned from having BPA, and in Canada last year they took the added step of deeming BPA as a toxic material, so this will be a call for further action in the future. For our study, we had 26 toys from discount stores or dollar stores, and we had a mix of toys, some toys with oral contact like these funny teeth or this snorkel or whistles, and then we had items that had possible oral contact. If you have children, you know things like the rubber duck and the army soldiers or even the doll's head will often go into a child's mouth, so there's a possible oral exposure in those toys. Before we tested our samples, we had to do sample preparation, which was the subject of our last webinar. To go over it briefly, we used cryogenic grinding to create a very fine analytical powder. This increased our surface area and allowed for a more complete extraction. We also did sample identification to group our plastics into the different types of polymers, and we decided to focus for this first set of webinars on what we perceive to be the most clean when it comes to phthalates and almost the most dirty polymers of the group. So PVC is notoriously dirty for different additives, polymers, phthalates, BPA, and some other types of compounds. HDPE is a much cleaner, it has less phthalates, and it's considered to be a cleaner type of plastic. We definitely looked at the standard test methods for phthalates, including the Consumer Product Safety Commission's method for the determination of phthalates. This method measures the 6 restricted phthalates and outlines the sample preparation, extraction, and the analysis for those phthalates. Now, the Consumer Product Safety Commission has a chart in their method that shows the different allowable analysis and extraction methods. And there's quite a few choices for an analyst to use. You can use sock slit extraction, pressurized fluid extraction, microwave extraction, ultrasonic extraction. There is also a wet method, which is in use by a lot of our customers. We do get a lot of feedback about this method, but it is intended for PVC materials, and that sometimes is overlooked because it's not clearly defined in the title that this is a PVC wet method. For this particular method, you need about 0.05 grams of sample and a minimum of 15 mils of solvent. We found with our toy samples, our PVC toy samples, that our samples didn't necessarily always precipitate with 15 mils of solvent. Here in this picture, you can see our certified reference material, which is basically just PVC and the 6 restricted phthalates and BPA. And then on the right, you see 2 numbered samples. Those are real toy samples. And it looks as if the 2 real toy samples would not precipitate with and I think this is actually 30 mils of solvent at this point. But I believe that's because of other additives that were in the real toy samples. So if you have to use more solvent, you're obviously going to dilute your sample more. And if you're looking at the limits for these different phthalates at the limit of 0.1% or 1,000 micrograms per gram, if you do a straight injection of a 15 mil dilution, you're looking about 3 ppm on your GCMS. If you dilute it further according to the method, you're going to be looking for about a target of about 0.7 ppm if you're looking at that 1,000 microgram per gram range. At 0.7, you're more than likely going to be using for GCMS a SIM mode unless you have a very new GCMS system that has great sensitivity to it. In SIM mode, though, we felt we might miss some of the other additives. We weren't just concerned with the 6 phthalates that have been banned. We wanted to see what else was in the material. And we didn't want to misidentify any other phthalates that might be in the material. There was also the possibility there was BPA or some very low-level phthalates, and we also did not want to miss those. So we decided to use scan mode. We also had some questions of what the extraction efficiency of this particular method was, especially since some of our customers had been using it for other materials other than PVC. So we started by taking one of our catalog CRMs for polymers, our CRM PE001. This is a polyethylene matrix, and it has the 6 restricted phthalates in it. And we used this material, and we followed the wet method, THF, to see what the recovery was for this wet method. And we got about, for our polyethylene material, about a 50% recovery. So then we changed gears, and we developed a new CRM for PVC. This PVC material, again, had the 6 phthalates that have been restricted, and we ran it through the THF extraction and precipitation method. And our recovery was actually pretty good, from 83 to 94%. We did run into a problem, however, with poor reproducibility, and we believe it was due to GC contamination. As we injected subsequent samples or subsequent injections of the same sample, we found that there was a variation between sample to sample, and we believe there was some GC contamination involved. When we looked at the RSD of the subsequent injections, the RSD for the different phthalates ranged between 35 and 60%. We then turned to microwave methods. We decided that since we had a microwave unit, a CEM Mars in our laboratory, that we would give this a shot at trying to do our extraction. We first looked to CEM's website, where they have an extensive amount of applications available. The first one we looked at, since we had our polyethylene CRM, was their HDPE method. And their method called for a cyclohexane and acetone mix of solvents. And when we did try our CRM using that method, we had about a 95% recovery of our phthalates. We also looked at an LDPE method with an IPA solvent mix, and we did also have in the high 90s recovery for that particular method as well. When we got to the PVC method, though, we encountered a few problems. Our first problem was the solvent matrix was ether, and in our laboratory we had chosen not to work with ether as our solvent, so we wanted to look for a different set of solvent conditions to extract our PVC samples. We looked again to the 2 previous polyethylene methods, and we were not really interested in running the acetone because we were afraid that the acetone would dissolve the polymer. And our goal was really not to dissolve the polymer. It was basically to swell the polymer, open it up with heat, and create an efficient extraction without dissolving it and causing that matrix to go into our extraction fluid. So we tried a bunch of different conditions, different solvent bases. Cyclohexane, IPA, and acetone were the 3 we did choose, and we ranged in temperature from a low extraction at about 100 degrees C up to a higher temperature extraction at about 150 degrees C. We found the best mix was in that green box there. At 130 degrees, at a 50-50 mix of cyclohexane and IPA, it caused the material to swell slightly. It opened it up, but it did not dissolve the PVC noticeably into the extraction solvent. And with this particular method, we got between 95 and 105% recovery. We did try a slightly higher temperature at 150 degrees. Again, we didn't see any dissolution of the PVC material into our extraction matrix, and we had very good recovery, 99% to 102. But we did find that there were some interferences with some of the internal standards and some of our other check standards when we ran this particular mix. So it was suggesting there was maybe a little bit of polymer at that higher temperatures that was starting to get into solution. So our final methods for extraction of our HDPE was prescribed by CEM's application note. It's 10 mils of cyclohexane at the 30-70 mix with cyclohexane and acetone, 0.2 grams of sample. We ramped to temperature over 10 minutes to 140 degrees C, and we held that for 10 minutes, and we did use stirring. For our PVC, we altered the CEM method. We kind of created a mixture of the different application notes that we had read. And we used 10 mils of cyclohexane IPA at 50-50 mix, 0.2 grams of sample. We ramped to temperature to 130 degrees C. And then again, we held that for 10 minutes. And again, stirring was used. And if you're interested in some of CEM's applications, this is their high-density polyethylene application note that we use. Now, they've designated it for antioxidants and slip agents, but it works perfectly well for the phthalates. When we compared our PVC method, we have, of course, the wet method for THF. We found that it did use quite a bit of solvent. And because if you were diluting it down according to the method, you were getting down to such a low ppm, we were afraid we were going to miss some of our additives. So we wanted a bit of a higher concentration. And when we did use it at a higher concentration without the additional dilutions, there was quite a bit of interference from the polymer on our GCMS, which did cause poor reproducibility. And it was a very time-consuming process to do each of these samples. When we did our microwave method, we did find it was more efficient for us. It was 10 to 15 mils of solvent for up to a gram of sample. We had very high concentrations, so we could see a lot of the small phthalates on GCMS, but then we could also dilute them down to a linear range for some of the very high phthalates that we did see. We found very little interference or carryover on our GCMS with great reproducibility, and very fast. Since we had the carousel with the multiple slots, we could do sample processing in multiples. If you look at the RSD data for the different phthalates that we were looking at, you can see that for the, again, for the CPSC or the THF wet method, you're looking at, for us, the injection reproducibility of about 35% to 60% RSD. For our optimized microwave method for PVC, we had less than 2.5% RSD. When it comes to running our samples on GCMS, we had a GCMS single quad in scan mode with a wide range of scan from 35 to 450 mass units. We used a typical DB5 or CV5 capillary column in a typical length. And we were able to separate most of our phthalates, with the exception being the two larger phthalates, the DINP and the DIDP, which do tend to overlap in the 14-minute range, the 14 to 15-minute range. For each of these, we scanned for 149, which is the primary ion for most of these phthalates. For bisphenol A, it was 213. The only exception was, of course, those two overlapping phthalates, and since they both had 149, we had to pick the secondary ion, which was 293 for the diisononyl, and the 307 for the diisodecyl. Now, these are examples of our HDPE toys, things like our plastic figures, our different military men and policemen. And some of our plastic car parts were also HDPE, notably the black base where the wheels were attached. The black wheels themselves were HDPE, and the silver interior of the car was also an HDPE material. When we looked at the different components that we found by GCMS, what stood out to us is of the 6 restricted phthalate, we really only found one, the DNOP. And we found that well below the limit of 0.1% or 1,000 micrograms per gram, the highest being about 130 micrograms per gram for the black car base, so the base where the wheels were attached. We did not find any bisphenol A. We did not find any of the other smaller phthalates. But we did find in one sample in our black car wheel, we found some higher alkanes. So we found these peaks of these higher alkane units in our GCMS for the black car wheel. Our PVC toys, we basically kind of broke them up into 3 groups. The first one being toys without oral contact. These were things like our cartoon figures whose identity has been blacked out to protect the innocent, and some of our other animal figures like our dinosaurs, our snakes, and our sharks. Then we had toys with possible oral contact, things like our duck and our doll's head and our lion. And then you, of course, have your oral contact toys, which are things like the snorkel, which are meant to be put in the mouth, or the funny teeth. The primary phthalate found in the PVC toys was DEHP. Now, if we look at the U.S. limit, which would be at most 0.1% or 1,000 micrograms per gram, if this is the only phthalate in here for the EU and Japan, it would be around the same limit. It would be 0.1%. But you're looking here now at that line, the U.S. limit, and you can see that most of our samples do actually exceed that 0.1% limit. Most notably, one that would cause me concern would be this snorkel mouthpiece. It's intended to go in the mouth, and it is somewhere around the 12 to 15,000 microgram per gram level, which means about 15 times higher than the limit for this particular compound. We also have other items that are, possible oral contact, like the doll's head or the duck, and they also are well above the limit of DEHP in the U.S. and the EU and Japan. The only oral contact sample that did not exceed that limit were those funny teeth, which just came in under the limit there. Another set of phthalates that we found in some of our samples, the second most common one was DNOP, and we did find those in 6 of our samples, but they were below that 1,000 microgram per gram limit. Our donkey was our kind of exception. He had 2 of these phthalates, the DINP and the DIDP, and in both cases they were about above the 1,000 micrograms per gram limit. And the DINP was reaching the 100,000 mark of micrograms per gram of the DINP. If we look at the total concentration of the 6 restricted phthalates for all of our toys, the blue line is the total concentration of 0.1 for EU and Japan. And then possibly in the U.S., if you have a restriction of 0.1 for each of the phthalates, that means the maximum limit you could possibly get to would be about 0.6 or 6,000 micrograms per gram. In either case, you can see most of the toy samples exceeded those limits. Again, the red samples are our oral contact toy, and there is that snorkel mouthpiece, which was clearly intended to go in the mouth, and it would exceed both the U.S. and the EU limits. If we're looking at our BPA results, we found 3 toys with a fairly significant measurable amount of BPA. Our Triceratops dinosaur with about 200 micrograms per gram, our friend Mr. Rubber Duck, which had about 700 micrograms per gram, and then our doll's head, which had close to 1,200 micrograms per gram of BPA. One of the interesting things we did find by using the scan mode is we found alternate plasticizers. Here are 2 of the alternate plasticizers that we were able to see in some of our samples, butyl citrate and then the tributyl acetylcitrate. For these 2 compounds, we found them in 9 of our 17 toys, and they were in very, very large amounts in 7 of our toys, in percentage amounts. The highest amount of these 2 particular compounds was found in our lion, and our lion was considered for at least the phthalates, the 6 restricted phthalates, to be pretty clean because it actually had none of the restricted phthalates, but it did have large percentage levels of butyl citrate and this tributyl acetylcitrate. For our PVC toys, we did see very small amounts of 2 of the other restricted phthalates, the DBP and the BBP, but both of them were under 50 micrograms per gram. And of course, DEHP, as I said before, was our most detected phthalate, where 15 out of 17 of the toy samples actually contained DEHP, and 12 of these samples, of these 17 samples, exceeded the 0.1% limit set forth here in the U.S. The highest amounts of DEHP were in these 4 particular toys. Our friend the rubber duck at about 28,000 micrograms per gram. Some of these toy sharks at 25,000 micrograms per gram. Our fake doll head at 21,000 micrograms per gram. And the disturbing mouth snorkel at 14,000 micrograms per gram. The lowest amount of DHP, which I said before, was our lion. It had no phthalates, but again, percentages of these alternative plasticizers, the tributyl acetyl citrate and the butyl citrate. Overall, the highest total phthalates was on our anonymous cartoon figure, and this was mostly due to that DIDP and the DINP results that we found. Of the oral contact toy, some of the highest results was found for that snorkel mouthpiece, and it was definitely way above the set limits. In our possible oral contact toys, our friend Mr. Duck was a big loser with high amounts of DEHP and high amounts of bisphenol A. And again, bisphenol A was detected in 3 of our 17 toys, with the doll's head having the highest amount at 12,000 micrograms per gram. In general, our HDPE toys contained very low amounts of phthalates, with only DNOP being detected, and that was lower than the prescribed limit. And unusually, we did find some of these higher alkanes in our extraction for our one part, that toy wheel off of the car. For our PVC toys, again, the DEHP was the highest of all the limits, but we did find the DINP, the DIDP, and the DNOP in some of our toys, and as well as BPA. And then we have the concern of these alternate plasticizers, or these alternate phthalates. We found them in half of our toys tested in pretty significant large quantities. Our follow-up studies are going to be on some of the alternate plastics and the alternate polymers we didn't cover today, things like our ABS plastic, our polycarbonate, and our polystyrene plastics. For our study, we did use a range of our Spex CertiPrep standards, including our catalog CRM for polyethylene, which I discussed how we used it as our extraction, to monitor our extraction recovery. And when that failed to basically monitor the recovery for our THF extraction method, we developed a new standard, a PVC standard that has the 6 restricted phthalates and BPA, and that standard is not currently available, but will be available by the end of the summer. That's a PVC matrix CRM, which does have these 6 restricted phthalates and bisphenol A. I would like to thank Spex CertiPrep chemists for all their assistance in this project, as well as the help of the CEM Corporation for all their input and assistance that they've given us with this project. At this time, I'd like to ask our guest from CEM, Bill, if he has anything he would like to say or any comments he'd like to make. Bill?
Thanks, Pat. Can you hear me okay?
Yep, we're good, Bill.
Great. Really great work, Pat. Just maybe a couple things that I would add or emphasize, and one is the importance of your cryogenic grinding. Being able to finally divide those samples is really going to be critical to get that surface area maximized as much as possible, and it's really going to help the efficiency of the extraction. So. And I think that proves out in your results and your reproducibility. Along with that, the importance, when you're going from that traditional precipitation method to a method where you're using temperature control, whatever method that may be, the ability to reproduce those results, and you can see it in your method development, is really dependent on being able to make sure that you can fine-tune both, your solvent mixtures, which solvents work best, and also reproduce your temperature from day to day. So, and the last thing that I would add is with any method, it is really going to be critical to have the good standards. If you're using a microwave, whatever method you might be using, the only way to be sure that you are indeed doing what you think you're doing is to be able to check using a good verified standard. along the way. So, but again, real great work, and I'm going to probably avoid snorkel mouthpieces in the future.
Well, thank you, Bill. We have a slide here for your CEM application support and your sales support, so if anybody needs some contact information, here is the contact information for CEM. And we are going to look at some of the questions now. I think I'll throw a few to Bill to start, but Matt has a comment.
Yeah, Bill, if you could just stay on the line. Everyone, we're opening up the floor for questions, so if you have any questions related to any questions directed towards Spex Sorter Prep, or we're keeping Bill on the line, so any microwave questions can be directed towards him. So just simply type them into the box, and then we'll get the questions answered.
Okay, Bill, we'll start you out with your questions so we can get them over with for you right away. Someone wants to know how they can access the application notes from CEM.
Yeah, simply just go right to the website. It's CEM.com, and we'll ask for kind of a typical registration, name, rank, and serial number. You'll establish a username and a password, and then you can access it under a learning support area, and it'll be simply titled Application Notes, and then there'll be a submenu for extraction. We do work with acid digestion and a few other areas, but you'll see a category that is listed for extraction, and then they are categorized, I believe it's under polymers specifically on the website.
Okay, and also, Bill, I know I had mentioned something before the presentation. We'll be sending out the slides this afternoon to all the attendees, so I can include a link in there as well to CEM's website, so we can link directly to maybe some of those application notes as well.
Great, great.
For all the the attendees today.
Sounds
Bill,
good.
A question that involves the microwave. Someone would like to know if there are compatibility issues with the different solvents or solvent mixes when using the microwave.
No, not really. No more than just the general precautions that you would use with any solvents. You brought up a good point, Pat, about about ether and the flammability issues and the fact that many people will try to avoid it. From the microwave standpoint, there really are no compatibility issues other than the general precautions that you would take normally. The key is, as you kind of pointed out in your presentation, is really finding the right mixture, the right combination, and the right temperature at which you start to open up your samples, but not dissolve them. But from a compatibility standpoint, all your solvents and the solvents that you're using would be compatible with the microwave.
Can you use partition solvents, Bill? If you have two incompatible solvents, would that actually work in the microwave to try to partition a sample's components into one phase versus the other, or do you not suggest using incompatible solvents?
That's a good question. You do have to watch, if you have any phase separation, and so I would probably not suggest that as a first step if you're going to have a compatibility issue, because you can get different heating rates of different solvents, and so if you have a separation in the system itself, what you might find is, and it'll depend on the stirring. The stirring can equalize that, but it would probably not be my first choice to have an incompatible solvents, partition solvents.
Okay, we have another question for CEM. Are there any guidelines other than beyond contacting you at CEM for some methods of development for different plastics or composites for work with the microwave?
Guidelines as far as just typical approaches?
Are there any published guidelines for working with the different polymers by microwave? Are there any methodologies published that you know other than your what's on your website and what you discuss with your customers?
Yeah, there's some reference papers on the website. I'm sure you would find reference papers. CEM is not the only microwave company out there. Is the one I'm partial to, but I'm sure other companies have done some work also in reference papers and application notes. Probably your best resource is to look towards the applications labs for the companies. You can contact us simply by calling the 800 number and discuss it with an applications chemist if there's a specific sample. Many times also we will run some samples in the lab if somebody is interested. So the combination of reference papers, application notes, and then really direct contact with the companies is really going to be able to pin down the method itself. And as is always the case, and we all know this, there is almost always method development involved whenever you're trying something new, or even something that is existing, as you found out, Pat.
Absolutely. I know I found from the experiences had working with CEM and working with these polymers, you have to have a certain goal in mind of what you're trying to do with that particular polymer, and then you have to look up its melting point, its solubility. That's where I basically started my methods development for the microwave method. I looked at the different polymers' melting points. I looked at how they reacted to different solvents. And my goal was not to dissolve the polymer. So I was picking conditions and solvent conditions which allowed me to, like I said, swell the polymer, open up the polymer, give it increased surface area and some permeability, but did not actually put that polymer into solution. So I tried to keep it at or below the melting point for that particular polymer, and then I did try to select a solvent system which might have been partially soluble with that particular polymer, but not completely, so it almost forced the equilibrium to keep it into its solid state. So it's a combination of speaking with you at CEM and a little bit of knowledge of the material and the chemistry and what I wanted to do with that chemistry that helped with the methods development.
I think that's a great approach. Understanding where the melting point is critical. Many of these compounds will be thermally labile above a certain point, and you can, unlike in some other areas of microwave sample prep, specifically digestion, where you can't really over-digest a sample. With extraction, you can over-extract if that makes sense. You can start to degrade your compounds. So it is really critical to understand, like you said, Pat, understand what it is that you're trying to pull out of these samples.
Okay, we have some questions here directed to Spex CertiPrep. Do you rely on a commercial MS library for identification, or do you have your own homegrown MS library? And there was a comment that there's been some library or identification questions with some standards. We have, of course, the commercial NIST library that we do use, but we also use common sense. We have found that sometimes in the standards, when you run a standard in a regular laboratory matrix like methanol or methylene chloride, it looks one particular way. But then when you add it to a real matrix or a real world matrix, some funny chemistry issues start to happen. In particular, I have noticed the flip-flop of one or two phthalates that when it's run in a straight type of standard, a matrix like methanol or a DCM, it looks textbook, but then when you actually compare it to a real sample or you spike it into a real matrix, something funny happens with the chemistry and the material that it's part of, and it causes a retention time flop of two of these particular compounds. There is also some question that is being raised about different source materials for some of the plasticides, some of the phthalate compounds. There are some compounds which have the same phthalate name, but when you look at the CAS numbers, they're different. So in particular, some of our larger phthalates towards the end of the chromatogram, they can have multiple CAS numbers, and that's because even though theoretically the structure is very similar or the same for these compounds, they have different sources for source material of how these phthalate materials are made, and they can have a different type of chromatogram. So depending on which type of phthalate you're looking for, what the source material for that particular material was, it could be a problem where the spectra looks a little bit different from the one standard to the next standard. And there can be some difference from different standard companies on which feedstock of these phthalates that they use. Which of the 6 or 7 plasticides are you most likely to find in toys? Well, of the 6 restricted phthalates, you do find the DNOP and the DEHP most commonly. We only did find the DINP and the DIDP in the one particular toy. And that's only right now for the two types of plastics that we have tested now. There is obviously the possibility of finding bisphenol A in polycarbonate toys, and as well as the PVC toys. And especially with everybody I've spoken to for the plastics industry, DEHP, DNOP are two of the big ones that you find a lot in the plastics materials. What model cryo grinder did we use? We used the Spex sample prep freezer mill. I don't honestly remember which model number. It is in our presentation from our part 1, and we'll be able to get you that information. But we did find it was necessary for us to use a cryogenic method for grinding, and it did increase the surface area of our particles so we had a more efficient extraction.
And I think that just about wraps up our questions. We did have an inquiry about some of our flyers and brochures being available in Spanish as well. So, Bill, I'm not sure, does CEM have any flyers and brochures available in alternate languages?
We do, Matt. I just have to check with our international group, but we should be able to supply something.
Okay, yeah, we do as well. We do have flyers in alternate languages, so we do have a contact on the call right now that would like that information. So, Bill, I could pass his contact information to you as well, and then maybe
that'd be great, Matt. Yeah, and I can take care of that. Make sure we get that information out.
And I think that's it. If you have any, if there's any further questions, you can send them to crmsales@spex.com. So before we let everyone go, I just wanted to announce 2 new products that we had. We now offer a full line of 1 ppm ICP-MS single element standards, as well as 2 new trace metals in the natural wine matrix standards. The part numbers for the wine standards are up on your screen. And if you'd like more information, please visit spexcertiprep.com. All right, again, I'd like to say thank you to Pat for giving a wonderful presentation, as well as Bill from CEM. Thank you for joining us on the call today. If you would like to contact us, please email us at crmsales@spex.com. And also, the first part of this webinar series, the sample prep of the plastic toys, is available to either download from our website or view on our YouTube channel. So again, thank you for joining us today. Bill, thank you. Pat, thanks. And we hope to see you again in a future webinar. Thanks,
guys.